Assalamualaikum and good morning. My name is Mohd Arif. My metric number DD240102. So, for the problem background objective, first, why did we choose this topic? In modern engineering, as buildings get taller, elevator hoist cable become extremely long. This length made them flexible and highly susceptible to transverse vibration, or what the industry calls rope sway. These vibrations are usually triggered by external forces such as high-altitude winds swaying the building or seismic activity. The danger here is resonance. If the frequency of the building sway matches the natural frequency of the cable will swing violently. This can damage the elevator shaft, destroy equipment, and endanger passengers. Therefore, our objectives are: first, to model the system using the 1D wave equation; two, to calculate the natural frequency to assess resonance risk; and the three, which is the last, to analyze how changing tension and length can improve safety. Thank you. So, for governing PDE and variables, we will talk about the engineering problem description first. So, for the engineering problem description, to analyze this, we define a specific engineering system which you can see in this diagram. We are modeling a traction elevator system with the following baseline parameters. The parameter is cable length. We selected 100 meters, representing an elevator park at the ground floor of a high-rise. This is the worst case scenario because longer cables are more unstable. Second, tension T. We use 15,000 newtons, which accounts for the weight of the car and the counterweight. And then the third is linear density. The cable mass is 0.3 kilogram per meter. Our goal is to predict how the specific cable behaves when it disturbed by a wind load. And then we will talk about the governing PE and variables. Now, how do we turn that physical system into mathematics? By applying Newton's second law, F equals to ma, to a small segment of the cable. We derive the governing partial differential equation. This is the famous hyperbolic 1D wave equation. Delta U square over dt square equals to c square times delta U square over dx square. Let me break down the variable. U, which has xt, is the horizontal displacement, which means the sway of the cable. X is the vertical position along the cable. T is time. C is the wave speed, which is mathematically defined as square root of tension over density. To make this solvable, we make three key assumptions. First, the cable is perfectly flexible, which is no stiffness. And the second, the mass is homogeneous. And the third is we neglected damping, which is the air resistance, to ensure our safety predictions are conservative. Thank you.
Okay, Assalamualaikum and good morning. My name is Muhammad Aimil Hilman bin Muhammad Syafiq. So my matrix number is CD240308. So my part in this group project is solution methodology. So I would like to share about the formula that we use and the calculation lah for this group project. So I would like to start with the objective, which is to solve the 1D equation for the transverse displacement under given boundary and initial conditions. And the chosen method is analytical solution using separation of variable and Fourier series. So as we can see in this picture here, you can see the formula. Okay, And then why we choose separation of variable? Firstly, because it is linear and homogeneous PDE, which is suitable for analytical solution, and it have fixed boundaries, leads to agent function expansion. And then this method yields an exact analytical solution in the form of an infinite series, which is physically interpretable as a superposition of vibration modes. Analytical solutions also allow for clear parametric studies and natural frequency extraction, which is essential for resonance analysis. So this is our solution and calculation. So we start with the general solution where the we assume the parameter which is L equals to 300 meters, T equals to 60,000 Newton, and mu equals to 1.2 kilogram per meter. Initial displacement is Fx equals to 0.1 sine um, pi x per L meter, and the initial velocity is gx equals to 0. So the first step is we compute wave speed, which is c equals to square root t over mu. It became square root 60,000 per 1.2. We get 223.61 meter per second. And then step 2, we compute the cn and dn. Um, and then we compute natural frequencies, and then for the step 3 we write particular solution, and then for the step 4 we compute the natural frequencies for n equals to 1, 2, 3, and so on. Okay, so basically this is our step 5, which is visualization using Python pseudocode. So our group use Python for this calculation to show all the graph. um, um, Actually, we have the input, we have the code, but I cannot put in this slide because it is too long. So, but in report, I already put it. So we have the output. So the output is wave speed, which is c equals to 223.61 meter per second. Angular frequency equals to 2.342 rad per second, and natural frequency 0.373 hertz. Okay, so in figure 4.1.1, we have a mode shape of Hoist cable initial time, which is t at 0 per second. And for 4.12, we have time history plot, which is displacement versus time. T also at time also at 0 second. And lastly, we have the figure for 4.1.3, which is 3D surface plot, space-time evolution. And for the natural frequencies, we have n for 1 we have 0.373 hertz, and then 2 0.745 hertz, and for n3 1.118 hertz.
Assalamualaikum and good morning. My name is Luqman bin Norhisham, now matrix CD240118, and today I'm going to talk about parametric study. In section 4.2, 4.2, we study how to changing system parameters affect the vibration behavior of the Hoist cable. The main objective is to understand which factor increase or reduce the natural frequency of the cable. In this study, two parameters are varied, which is first is cable length and second is cable tension. The linear mass density is kept constant, so the effect of each parameter can be clearly observed. First effect of cable length. When the cable length is increased, the natural frequency decrease. This happens because longer cables are more flexible, they require less energy to vibrate, and they oscillate more slowly. Mathematically, this match the formula Fn alpha 1 per L. Physically, this means long elevator cables in taller buildings are more prone to lower frequency vibration, such as those caused by wind or building sway. Second effect is cable tension. The next cable tension is varied while keeping the length constant. The research shows that increased tension increase the natural frequency. This is because high tension produces a stronger resonating force. The cable becomes stiffer and it vibrates fast. This, this agrees with the relationship Fn alpha square root T. So here's our finding. In case 1, we put vary L and the tension is 60,000 Newton. As you can see, longer cable have significantly lower natural frequency, making them more susceptible to lower frequency excitation like building sway. In case 2, varying T, L is constant which is 300 meter. Observation increased tension rising natural frequency which can move the system away from resonance with external low frequency source. For engineering interpretation, from an engineering point of view, cable length is usually fixed by building height, but tension can be adjusted to control vibration behavior. Therefore, increasing cable tension is one practical way to shift the natural frequency away from resonance, improving safety. That's all from me. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. I would like to introduce myself. My name is Muhammad Arif Hazim bin Azhar. My number matrix BD240070. I would like to present about result and discussion, which is first subtopic is computational result. In this section, we analyze the vibration of the hoist cable using the one-dimensional wave equation. First, the wave speed was calculated based on the cable tension and linear mass density. Using this wave speed, we determine the natural frequency of the cable for different vibration modes. The result shows that the fundamental frequency lies below 1 Hz, which is expected for long elevator cables. Higher modes increases proportional with the mode number, confirming the correctness of the analytic model. For the second subtopic, which is graphical visualization of cable vibration. To better understand the physical behavior of the cable, graphical visualization were generated using Python. The displacement versus position plot shows a sinusoidal shape with zero displacement at both ends, satisfying fixed boundary condition. The time-dependent animation demonstrates oscillatory motion about the equilibrium position with constant amplitude, due to the assumption of negligible damping. Additionally, the 3D surface plot clearly shows how displacement varies with both times and position, confirming the harmonic and wave-like nature of the vibration. The third subtopic, effect of system parameters. That has two effects. The first one, effect of cable length. This parametric study examines how system parameters affect natural frequency. First, as the cable length increases, the natural frequency decreases. This happens because longer cables are more flexible and require less energy to vibrate. As a result, long elevator cables are more susceptible to low frequency excitations such as building sway. Next, effect of cable tension. We investigate the effect of cable tension. Increasing the tension leads to higher natural frequency because the restoring force in the cable becomes stronger. In this case, the cable to vibrate faster Therefore, adjusting cable tension can be effective engineering method to avoid resonance problem in elevator system. Continue with subtopic engineering interpretation and safety implication. From the result, we can see that long elevator hoist cable in high-rise building have very low natural frequency. This is important because this frequency often fall within the range of wind or seismic excitation. When the excitation frequency match, the cable natural frequency resonance can occur. This resonance can lead to excessive cable sway, which increases the risk of contact with shaft components and accelerates fatigue damage. Therefore, from an engineering and safety perspective, it is essential to manage cable tension properly, use vibration dampers, and carefully consider cable length during elevator design. Even with a simplified model, these insights are valuable for ensuring safe and reliable elevator operation. The last subtopic of result and discussion, which is limitation of the model. Although the results are physically meaningful, the model includes several simplifying assumptions. First, it assumes constant tension along the cable, whereas in a real elevator system, tension varies due to the cable's safe weight. Second, damping effects are neglected, even though real systems have damping that reduce vibration amplitude. Third one, the model assumes small transverse deflection, which limits its accuracy for large motion. Despite this limitation, the simplified wave equation model is still suitable for preliminary design and resonance assessment, providing useful first-order guidance before more detailed analysis is performed.
To conclude our study, basically, we use the 1D wave equation to model how the cable move. Our Python and MATLAB simulation show that in the tall building, this cable vibrate at very low frequency and usually less than 1 Hz. This means they are flexible and prone to swinging. For the length and tension, we found two main rules here. The longer the cable, the lower the frequency. This makes tall building more at risk during the earthquake or wind. And the higher the tension, the higher the frequency. We use tension as a lever to pull the cable out of the danger zone so it doesn't vibrate uncontrollably. For the safety and final recommendation, why does this matter for real world safety? If we don't control this vibrate, we risk rope sway. This is just a comfort issue. It can lead to the cable hitting the elevator shaft or damage the steel strand, which is catastrophic. Even though our model is a first order estimate, is meaning we simplify things like bending stiffness. So if we give us a clear roadmap to ensure high risk, the rise elevator are reliable. Engineer must focus on three things: adjusting tension, integrating dampers, and constantly monitoring cable length.